Okay, let me just take a moment and introduce Gilly. And I didn't really prepare anything, just to say that we've been having these wonderful talks, and I have been so impressed by what I have seen you doing with the solar image processing that I thought this would be a great this is a more informal science discussion. But Gilly, you're at Southwest Research. Why don't you start by giving us a little bit more information about yourself and take it away?
Like Sarah said, I'm working at Southwest Research Institute right now here in Boulder as a postdoctoral researcher with Chris Lauder and Dan Seaton and Craig DeForest, who are names I'm sure none of you've ever heard. I'm mostly doing, my thesis title is this spectroscopic analysis and image processing of the optically thin solar corona. So I just like sort of thinking about light when it's interacting with matter, especially when it's transparent, how you're trying to look at different things and understand what is going on in your image. My thesis was more about like the optically thin nature of the corona and how that affects images. But we're going to talk about a bunch of other things today. This talk could have gone in one of 6 possible different directions. And so I settled on under a little bit of advisement, this sort of a schedule here, an agenda of just sort of a primer on the types of data that we're looking at, and then like some interesting methods for processing the data and what that does and what the data is able to be used for after that point. And then what's the difference between processing data and visualizing the data? Why do we need to visualize the data? And if we have time at the end, I've just listed some cool modern like SunPy and other Python related tools that make some of these things easier. It's about 40 slides for about 50 minutes. Definitely feel free to speak up if you want. This is supposed to be a discussion rather than just a complete me talking forever. But I will just talk forever if nobody asks anything.
You continue. I'm going to try to put it full screen.
Oh, thank you.
I think maybe that's the spot.
And so I'll just truck forward here. So the sun is hot. We know this. But there's lots of things that we don't know about the sun. An interesting thing that I learned is just how black underneath the sun is for most of these wavelengths. Like when you look at it, it looks like there's light coming from the entire disk. But if you were to just go a little bit deeper, I don't think that the sun is really emitting very much light in these ultraviolet wavelengths from the photosphere. So that's kind of an interesting little bit. I mostly look off-limb and have so far. So understanding that it doesn't like go the foreground and the background or like how that all works. It's sort of different in those two states. So again, there's a lot of directions I could go here, but I'm going to try and stay on the rails if I can help it. So another good option for full disk imagers. So there's a couple different kinds of images. And in this case, SUVI is what we're sort of relying on right now because the JSOC, if you haven't heard, is currently underwater. Literally. So they're rebuilding that and they have lots of their petabytes and billions of files still safe on magnetic tape. So that's great. So what other kinds of images do we have and what will we be talking about today? Coronagraph images, again, something I'm sure that a lot of you are familiar with, where you're blocking out the sun and then trying to see as close to the sun as possible. This is sort of the opposite idea to the full disk images, where you're looking at the sun and trying to see as high as possible. Both of the situations are made much more difficult by the extreme contrast in intensity. So there's difficulty in measuring it, there's difficulty in visualizing it, there's difficulty in understanding it. And in general, I don't think people are really used to dealing with 9 orders of magnitude or whatever it is, difference in any quantity really in a way that is understandable to humans' brains, I think. So what's missing in these images? Well, I just wanted to talk to how do you go from the image capturing moment to I have data on my computer that I can process, and what are the different steps that you have to take? I don't want to spend a lot of time on the processing levels, so I'll just sort of outline the high level what is done there. If you want to know everything there is to know, the paper in 2010 by Marcus Schwanden, is amazing. It just tells you everything you would ever need to know about processing images. So definitely check that one out. In general, when you're going from an instrument-like piece of data to a science-like piece of data, you're going to have different levels of processing that have consistent steps that have been taken, and those steps will be outlined in detail. So in the case of AIA, which is the main instrument that I've used, the atmospheric imaging assembly, you start with level 0, which is just sort of an integer per pixel. It's not related to I mean, you know, it's related to the real signal that you're getting, but it's not in physical units at all. It's integers in an array. And there's a lot that you have to do. With the level 1 data products, usually they try to get out all of the physical instrumental effects, flat fielding it. If there's any kind of a gradient across the thing, you'll take a dark frame to try and see how all the different pixels are behaving under a no light situation, and try and remove any of those effects. Also, the physical units are typically calibrated at the level 1 point. 1.5, again, just in terms of the atmospheric imaging assembly, really is about data set calibration, co-aligning them, making sure it's not rotated slightly, making sure every pixel is in a consistent location in physical units rather than just some sort of a spacecraft that's kind of tilting around and trying to station keep and such. So the level 1.5 data is really where most people, I think, who aren't instrument people are going to be starting with AIA and with science data in general. That's kind of where scientists start. There's one level above for just like generalized. I feel like the level 2 products tend to be like, this is the line width everywhere, this is the Doppler velocity, and it's something where you maybe do a fit and you get a parameter out or some other inversion or derived product. And with Punch, I think we're going up to level 3 because then you derive things from those derived products, is my understanding. I'm getting nods.
Yep.
That seems right.
Fields, for instance.
Sorry.
Flow fields.
Right. Yeah. So mapping the like a dense map of where all of the different velocities are across the field. Yeah. So there's a lot of interesting data products get there, but that's not exactly image processing per se, as it is like we made this instrument and we're going to try and get the instrument out of the data and hand it to the scientist, which is extremely important. And I don't want to devalue that at all. For sure. The thing that I know a lot about is the dynamic range issue, trying to image things that you really can't display in one image without doing some sort of processing on it. So let's sort of look at what that normally looks like. These are 2 typical AIA images at the level 1.5 level of processing. So this is typically either this or the square root of this, depending on how you're displaying it or printing it. This is typically where people start with AIA imagery. And if you're trying to do anything that involves absolute intensities or ratios of intensities or anything like that, these kinds of algorithms that I'm going to show next aren't good for that. But if you just want to be able to see what's going on in the image, flow tracking, like you mentioned, they're absolutely fabulous. So like I said, this is just like a logarithm. And it shows that there's actually a ton of information up there that you're not even visualizing at all when you're doing this in the top left plane sort of implementation. And if you use something that's a little bit more advanced, I'll talk about the radial histogram equalization method that I've come up with. And you can really maximize the contrast a lot more than what you can get in the typical display. I wish that I had gotten this out early enough to have somebody consider it to be a postage stamp. That was a cool moment a few years ago.
I have a quick question.
Of course.
So the 1.5, it's still in data number. The unit's not like physical. It's still data number, right? The unit.
My understanding is that at that point, it's trying to be something like ergs per like pixel area per time, something like that. So maybe it's trying to be closer to a specific intensity. If anyone has clarification on that, one of the steps of the level 1.5 processing in the AIA_prep IDL routine is that I believe that it gives you the per second values. Do you have something, Sarah?
No, keep going. I'm just
Okay.
trying to get rid of the thing in the bottom right.
Oh, okay. If the 1.5 doesn't do that, that would be interesting. I think that it would probably make videos flicker maybe more than it's doing when I see it. So I suspect that it's photometrically calibrated at 1.5. I'm getting some nods. But yeah, definitely anyone, if you have any questions, I can just keep going through this quickly. But if I'm going too fast or too slow, glad to change this up in any way that makes it more of a discussion or more engaging for anyone. Right. I wanted to point out a couple other data sets and what can be done with them. Again, just because AIA is currently not being used. So SUVI is also just wow awesome. Dan Seaton did these off-pointing campaigns and those were fabulous. But you don't even need to do that to see that you can get data out to the edge of the detector, and it's very likely that you'd be able to see things higher than that. I think when you use some of these radio filtering methods. So I'm going to talk about what are the different kinds of methods next, but I think I might have one of, no. Okay, so what is making it difficult to observe these? Sorry. So what we're looking at here, there's a lot of these that are going to be shown in different ways. So I'll just explain it a little bit more in depth here. So we're looking at intensity on the vertical axis as a function of the distance from the sun center. So we've got the sun center on the left there, and we've got the limb there around in the middle. And you can see that the intensities in this histogram, and it's a subset of the pixels at each height, it dramatically drops off by several orders of magnitude after you go off the edge of the limb. And so when you have a picture space that has 0 to 256 values and approximately an 8-bit integer for most display technology, that's not enough values to display this without approaching it in some manner. You might try to compress it to like only integers. You might try and do a bunch of other techniques that we'll talk about. But here's the best sort of like explanation of why it can't be done without some sort of processing. In this case, this is what I call the quantile radial norm. Instead of just taking the mean and subtracting it or dividing it out, I actually used the whole data set to find percentiles at each height. And so this is something like the 5th percentile, the 30th, and the 60th, and then the 95th or something. I couldn't tell you which numbers I used, but by doing that, you're able to capture the maximum dynamic range in the green top and the bottom, while also getting the most likely pixels to fill more of the dynamic range. So I'll just show what that looks like when we use those curves to normalize these data. And what you end up getting is something that's more like a 0 to 1, and it's more space filling in the dynamic range. So anywhere that you look in the image, now you have the opportunity to see something dark and something light. And so that is what we talk about when we're talking about histogram equalization or bending in any way there.
Can I ask a question? So can you go back to the image where you show your version versus kind of the classic version?
Yeah. For this one?
So yeah, so you're putting this, you're filtering it in such a way that, as you say, you can see, yeah, you have the range to see everything. Is it constant on a given height? So in other words, if I'm looking at something at a height compared to everything else, all the different latitudes at their height, they're all at the same range. Is that true? This is a radial filter.
It's radial, yeah. So it's distance from the sun center as opposed to like an azimuthal, like position angle or something.
Okay.
But like everything in a given radial distance is being considered in one set. And I can show you the function that I use on that.
Yeah, okay, go ahead. Thank you. I just wanted to make sure I understood that.
Yeah, of course. I thought that I had an overview.
One other question, once it's normalized, that is a linear scale, no longer logarithmic?
This is now linear, yeah. Sorry, that would be a good
No, you could.
thing to mention. Thank you. Yeah, so exactly, here we are. So what are the three main categories? So as I did a literature review and I looked at the way that people talk about it, and I listened to people talking about it, I think that there's three specific families that of different like approaches to the problem. So I'll just show by example. So there are the radial graded filters, and specifically what the radial graded filters do is they take advantage of the fact that there's a radial symmetry, and they take some sort of average or some statistic as a function of height. They use that statistic to normalize out the data. So in general, if you're using the idea that it's a circle and it's got a radial fall off, that's the radial graded filters. And the normalizing radial graded filter is the most common one to be used in literature. A lot of these other ones are great and they make sense theoretically, but they don't appear very often yet.
And I believe, and maybe Juliana or Ben can confirm, that the one that we use for Mauna Loa data online is the NRGF.
It is. Yeah, I stole pictures from your website to use it a little bit.
Cool.
So it is, yeah. And I'll show.
You mean that's for the K core?
Yeah. Maybe also for the compi?
I got the K-Core video and I did it through NRGF and I did it through RHE both. And I'll show both of them here in a bit. So they're pretty similar, but I'll show some details in the difference. Okay. The adaptive histogram equalization or histogram equalization in general is just the idea of messing with the values by ranking them or reordering them, or saying like, regardless of the geometry of the situation, let's take a neighborhood and in some way change around the histogram of that neighborhood to better reflect the dynamic range in that local region. Typically in normal imagery, people will do it with little squares tile across the whole thing. The cool thing about the method that I purport to say is nice is the radial histogram equalization uses annuli. as the neighborhood. So everything at that height has the same like mean from the radial drop off. So because of that, you can just treat it all like one neighborhood, and that immediately pulls out the radial gradient without even having to do a traditional radial graded approach. So it really is sort of a hybrid method because it's using histogram equalization as its methodology on a shape the same as a radial graded filter. So that's where they kind of can overlap a little bit in terms of the different families. Does that make sense at all?
I think so, but are you saying that some of the other ones that don't have the word radial in them are not radial filters?
Adaptive circular high pass filter, I'm not sure that it is radial or not. It seems like it because it's got the word circular in it, but like the noise adaptive fuzzy equalization and the variable neighborhood version of that don't inherently take care of the radial, I don't think.
Okay.
Now, it turns out that a lot of these methods do address that issue, even if that's not their approach. So like multiscale Gaussian is really good at pulling out coronal features, even though it's not directly aware that it's pulling out the coronal. So multi-scale methods are sort of like a Fourier transform is a good prototypical example. You're decomposing your image into a different basis set. You are modifying the amplitudes of those bases, and then you're inverting back to the original. So in multi-scale Gaussian norm, it's sort of like an unsharp mask takes an image, finds the blurred low frequencies, and then subtracts that out of the main one, and that's how you have the high frequencies. So an unsharp mask is actually removing the low frequencies to give you a sharpening. In the same way, multiscale does that. They blur the image at a bunch of different scales, and then they change the amplitudes and then recompose it back together. It requires you to know the size of features that you want to be amplified. So that one does come pre-built with some tunable parameters for that. And one of the goals of my work is to make the tunable parameters be things that are an intuitive, more physical kind of parameter. So RHE has a parameter like that I'll also talk about briefly. So now I'm going to show a bunch of pictures of just what they look like and maybe talk a little bit about how a couple of the methods work. If anyone has any questions before I jump into that, though, I'd be glad to take any. Cool. So the quantile radial norm, this is just sort of a thing that I was playing around with. I feel like it's sort of an intermediate result that got me to what I ended up doing with the RHE. But like I said, you make several different curves and you try to normalize that out. It gives you something that looks like this, which is a lot higher contrast for sure. You can see a lot more features than you could before. But there's also a ton of radial artifacts, and it's not necessarily very robust against like the fact that this particular bit is quite bright. You can see over here that a lot of the other things at that height are darker than they would be otherwise. So it's not as resilient against really oversaturated regions as I would prefer. So with RHE, the way that it works is you just sort the pixels by radius. So that's binning them by radius. Then you sort them again by intensity. So we've got the least intensity, we can call it 1, and the maximum intensity, call it 1 billion. And then we rank them by index 1, 2, 3, 4, 5. It doesn't matter what their actual difference is. We're going to make the difference between every pixel be the same by making them integers, and we're going to increase by 1. And then you just normalize between 0 and 1. And now every pixel is between 0 and 1, and there are no regions with more density of members. So the histogram is flat. That's why it's called the histogram equalization. And that's what you're seeing here, where it looks sort of like white noise. Again, that's because it's a subset of the data. If it were not, it would take 1 million years to load that image, and it would just be black. So this is what that one looks like. A lot of the things that, to my eye, were really sort of garish in the last one are gone in this one. You don't have that really hard line at the detector edge like we had before. This region is significantly less oversaturated here, and even the dark regions are less undersaturated. But this still felt a little bit harsh in terms of just like, I want to present this to people and have them think it looks cool kind of a perspective rather than a science perspective. So we developed a a function to, here it is. Developed a function basically, instead of mapping it to a flat distribution, you map it to a more centrally, more of a Gaussian distribution. And the idea here is it's like a gamma correction where you map the input values to the output values, and you just put a curve in there so that it's not a one-to-one mapping. In this case, the high side and the low side are given the same value, but basically if one of the values is set to 1, it's a one-to-one mapping, so you're not affecting anything at all. If it's set to 0, everything on that half is set to 0.5. So the idea is you pull things towards the mids and away from the extremes when you do this. Another way of thinking about it is if it's oversaturated, you pull down the high one and it undersaturates the high stuff. Or if it's too dim, you can turn down that one. You can turn down the blacks and they become a little bit grayer. So this is when I was talking about trying to come up with a more intuitive parameter to try and change. In my opinion, this one is just like, do you want the things that are light to be less light? Aside from that, it's able to do everything without any parameter tuning or understanding of what you're looking at, really, except for where the center of the sun. The center point of the sun is a big one. If you miss that, it kind of messes up the whole thing. Yeah, so I just wanted to show one or two more of these pictures, and then we'll get to another section. So like we were talking about before, multi-scale Gaussian is a really cool method. It's been used a lot. If you've ever seen an eclipse picture with those awesome corona images all around it, it's probably processed using MSGN. It's not explicitly a high-pass filter, but effectively it's more of a high-pass filter. You don't get as much variation in the highs and lows. But I think it's interesting that, again, without telling it anything about the fact that that's the edge of the limb there, it is able to significantly increase the dynamic range that's being used. The available dynamic range is being used better here. And the point of this section is just to say that you can actually take the average. And so we can see in this one, you've got a lot of those well, you probably can't tell in this as well, but it's a lot more fine detail is still there while not getting rid of the lower frequency details quite as much. So that's something you can play around with. And I just want to mention that all of these filters are all currently implemented in SunPy, SunKit image. You can use them today. You might need to get the latest release rather than the stable release or something. But if you want to play around with any of these things, they already exist.
Have you tried making movies out of something like this to see?
Glad you asked. Yes, for sure. I think I'll just show this histogram thing real quick, and then I think I've got some more results like slides. So just to point it out again, it looks like we've got a half hour still, so I think we're doing good. I've got the images here at the top. I've got the mean and the standard deviation of each one as a function of height. And then at the bottom here, the original histograms as we were looking at them before. So those are just a scalar transform. You applied this to every single pixel the same way. You don't have to worry about anything in the image. And it does something at least for the log or the square root or whatever you want to do. Radial graded filters do pretty good, excuse me, at trying to even out the image so that it's the same statistically everywhere. I'll point out that the non-radial graded filter on the right there has a really nice, really flat average as a function of height. And it's sort of optimized to do that. That's its deal. It's not a perfectly flat line, but it's really good at that. But notice that the actual histogram isn't necessarily equalized because that's not what it's working on. It's just working on the gradient there. So that's different than a histogram equalization method like this one, where it specifically sets that to a flat 0.5 is that mean as a function of height everywhere. Which is nice to have something that can normalize your whole data set from 0 to 1 with a mean at 0.5 and a nice low variance. And just to point out again that the epsilon redistribution does lower the standard deviation slightly there because we're clustering it a little more towards the mean. And then there's all of these other multi-scale ones, which are in combination. I think if I have any more examples of pictures, I might skip through them a little bit to get to more. Nope, there we go. Content. Exactly where I was done with it. Perfect. So yeah, let's talk about some of the things that you can and can't do with imagery like this, as long as we're all still good with trucking forward. Okay. So one really cool thing is these composite maps. People have made these before, of course, and they look kind of similar to this, but I think it's really fun to be able to see like not just that the polar crown filament is there and that it persists for a long time, but to watch it, especially in a video form, which I can show at the end if there's time on this one. This is just here for me to point out one more time, never take ratios of these values to try and get anything. Never, once you add or subtract or divide any arithmetic to it, it becomes invalid. Even subtracting, I thought it was just if you divide it or something, but even subtracting like 10 minus 5 and 5 minus 5, now you've got 5 over 0, which is not the same as 10 over 5, which is obvious. But I was just like, oh, yeah, really don't take ratios of things once you've done arithmetic on them or any other nonlinear transform. So that's one takeaway here.
So this composite map, you've got 3 different wavelengths of
That's
light,
right, yeah.
and you're just overlaying them, or?
Basically, it's an RGB image.
Okay.
And so each of the channels is 0 to 256. And so if you take your whatever it is coming out of the instrument and get it into a unsigned 8-bit integer format, you can assign to the R, G, and B channels separately and just have a 2 by an additional dimension array. And that will make you a nice RGB image. Yeah, there's a function called like Lupton _ RGB, and it's not Lisa Upton. It was someone named Dr. Lupton or something a few decades ago who came up with this algorithm to do it. But the point is, yeah, you can composite together basically any 3 images that you want. If they contain data at the same spot that matches, it looks more real. If it's like the 304 channel with anything else doesn't make images that look super real because you have like a magenta sort of smudge and nothing really, it's just a magenta smudge as much as like, whereas here you're like, oh, that's a filament up there. Or this is, wow, this is another great example of on my screen that is significantly less oversaturated than it is there. So that's another thing to point out in terms of displaying is that you never know what's really going to come out of your display technology until you get there.
Which type of filters did you use to make the each composite?
This is 171, 193, and 211, the pink one. Yeah.
Which method did you use to?
Oh, right. This is mine, the radial histogram equalization. Yeah. Before that, I guess there's lots of images like this. Well, they will be again on JSOC at some point. And they mostly don't go particularly high over the limb. In general, I think that AIA is underutilized for off-limb science because there's just tons of stuff going on there. The videos. So this is one of my favorite videos of the sun. You've got this thing here, and it does some sort of transformation there, morphologically, and then something
The CME.
down, and then this happens, whoosh, and then we get this like ribbon arcade structure that goes down. This is one of my favorite time periods. I made a mouse pad out of this this image of the sun here. So there's that one. And then of course, if you want to watch it go faster, so this is like 10 minutes, no, 30 minutes per second or something. This one is much faster. And what I think is really cool is you can really start to watch these long-lived features kind of go around and around. Sometimes like you can't really tell if something's in the foreground and the background, but when you start to go faster, with higher frame rate than you can probably see here. Oh, wow. Looking at the screen is a little bit sad. I'm going to keep looking over here. Yeah, so that's just to say that I personally watch the sun with my own eyes on a screen for part of every day, just because I like to, oh, I've never seen that particular thing before. And so just in general, I think that a lot of solar physicists don't necessarily look at the sun very often.
Gravity is really rotating. The one on the left while it's erupting. It's really clear. You couldn't see that before. I never saw that.
Yeah.
You know that.
Yeah. So there's a lot of like that cavity. There's a CME, that thing you saw. That's a cavity lifting off on the top right.
Yeah, and it's spinning. You see, I never seen that.
And you see on the right, that big movie. There's another one that's about to do the same thing. And you're right. It has a twist as it goes. And I don't think I've ever seen it quite like that before. Hey. Oh, now is it going to come back, or is this repeating or not? The one on the right.
Oh, it is. It's just like a decade or something.
It's a decade. Okay, well.
Right before the JSOC went underwater, I downloaded like one frame every 6 hours for 10 years or something.
Good for you.
It was awesome. So I'll try and pull that up
Do you
later.
mind starting it at the beginning again? Because I want to see that. Yeah. Okay. And what's the time? What year?
We're looking at 2013. in January.
Okay.
I think that I conflated 2013 and 2003. I've been trying to look for the Halloween storms in 2013. I don't think that's a thing. I think it might.
That's 2003.
Yeah. So I don't think STO was there.
Uh-uh.
No. Okay. Which is why I haven't been able to find it.
That's fine.
Makes sense. But yeah, and Sarah, if you want to look at this in higher quality afterwards, it's significantly nicer on my screen than the blockiness you're seeing over there.
That's pretty cool.
So let's go to another couple fun science things that you can do with it. Here's LASCO. I figured that you all might be the people to ask. So unfiltered, obviously you don't really get much out of white light like that. But when I put RHE on it, I get these two, major lobes here. I'm wondering, is this zodiacal light? Is this one of the various lettered coronae? Is it dust in some way?
What's RHE?
The radial histogram equalization. Yeah.
That's yours.
Yep. So we're bringing out the fact that there's some sort of radial feature, and I'm just not entirely sure what it is. I mean, I assume it's aligned with the ecliptic, right? So if anyone is an expert in that, I would love to know what that is.
I guess it's hard to understand. I don't understand your method well enough to understand how the thing on the left became the thing on the right.
Yeah, that makes sense. Oops. Spoilers. Yeah, so at every point in the circle, it picks what is the darkest, so that's going to be black, and what's the lightest, and that's going to be white here. And so since there's a gradient there from the darkest to the lightest, we're going to get that. Oops, clicking it again. We're going to get that much more sharply than we would have beforehand.
One thing you might look at is there's various models of F corona.
Yeah.
I know you can do it in SolarSoft Ideal. I imagine they have something like that in SunPy. They're based on, I don't know, I think, was it Philippe Lemay or somebody did this for LASCO a long time ago. You could take those models and just like synthesize it and then run it through your thing and see if what you get looks like the thing that comes out of an F corona model.
That makes sense, yeah. And I suspect that if the processing that happens after this point, again, I don't use this instrument very often, but I suspect that they take the thing on the right and use that in some way as a background, or if not the exact thing on the right, like you'll find a background and subtract that out and then try and get the.
Yeah, I think the way LASCO used to do it was to take like a month's worth of observations sometimes and subtract it out, or else you do a fit and then you subtract out the fit. Yeah, somebody online might know more about this.
It's nice to have a single shot method. The RHE, I think, is one of its strengths is also that you can apply it to a single image without any prior knowledge about the image, and it'll make it all be the same because of the histogram equalization. It's going to have a 0.5 mean and the same statistics across the whole field. So that means even if you don't know anything about it or sequential frames, they shouldn't flicker in a video because the averages are the same everywhere. And in my experience, I've never seen any flickering from that. Like a flare goes off and the whole image flickers or something. It seems kind of robust to that.
But can you use this to get rid of the F corona?
It depends on if that's what that is, and if that is a signal that I think you might need to average if you want to really subtract it out, because this is just going to be an instantiation of it. But I think you would have to average.
Well, the F corona is pretty stable, but yeah.
Nice. This is excellent Earl Grey.
Isn't it though? The honey is what makes it.
Okay, so this is, I think, actually some of Sarah's work that my advisor Chris Lauder handed to me and said, would this look good in a filtered? So this is the Gamma model that was then forward modeled with forward using the punch field of view and data processing pipeline in some manner. And then I got it after that, and I just applied the the normalizing radial graded filter, the very popular one, and then mine, the RHEF. And they're not super different. I would say that the biggest differences here are that the RHEF is a bit sharper in terms of the gradients. It also goes a little bit deeper, so you get the actual the darkest color here, whereas that color doesn't really appear anywhere in the normalizing filter here. Again, just because it's not really attempting to optimize for that. So that's not necessarily a weakness so much as just it's not necessarily doing that. Another thing I wanted to point out is that there are some features here that are not real in terms of real data, but I think that it's real in terms of the forward voxels potentially.
Hmm.
That's kind of what we're hoping is what those little, because otherwise it's like gravity waves, which doesn't make sense because there's no waves
So
in
this
this.
is looking down from the pole.
No,
I don't believe so. Yeah.
no, but it's looking at a fisheye camera type view. You don't have a flat plane of sky,
Right.
so it changes things
The pin cushion.
Okay.
the way what you might expect about like spiral structures and so on.
Interesting that you've got like a positive and a negative pin cushioning.
So what you should try to do is to rerun this with the number of line of sight points in your forward integration, double it and see if any of that goes away.
Hear that, Chris? Yeah, no, that's a good call. Or if it doubles and then the wavelength of the artifact changes.
Exactly,
then,
exactly.
So that's that. I was told recently that talking about this might be a fun thing to do at a future meeting as well by Sarah.
Yeah.
So here's one that you guys will definitely recognize, I think. So the main difference is that I couldn't get the same like 2-minute versus 10-minute average, but I think aside from that, everything else is the same between these. And on the left is using the NRGF, and on the right here is using the RHEF. And I'll just start them both. And it should just loop for a while so we could talk about different things in it. I like the Newton's rings thing that shows up in this. I suspect it wouldn't show up in just a flat representation. One of the cool things that I've noted is that you can really kind of pull out the polar plumes a bit better.
Yeah.
Which I think is pretty cool. I'm not sure if it's because I feel like a 10-minute average versus a 2-minute average isn't enough to explain the difference in those. There, like the plumes shouldn't move that much more that the contrast is gone. That's an opinion. I'm not sure if that's actually true.
Well, hang on.
Sure.
Am I seeing blobs go off the top and are they real?
On the right,
Yeah.
I think that this might be real movement.
So this is like what we see in the ISRM thing that Greg did with the difference, he goes out to, that thing where you're seeing the flows coming in and out,
Yeah.
that we can see that kind of flow with K-core.
Yeah, I think so.
Dang.
Isn't that just the optical fringe? Moving?
It could be. Is this white light or what?
Yeah, I was
Shouldn't be
thinking
too-
about the same. I'm not sure if those blob may be an artifact or maybe some fringing. We need to look into that a little bit more.
Sure.
Yeah,
Yeah.
I mean, does seem like it has the same sort of spatial frequency as the fringes.
But the motion,
Disconnects.
yeah.
Question
Yeah.
is, does the motion go down here?
Yeah, I'm not sure it's real motion in the sound though.
Be interesting to look at more.
Yeah, and with a bit more of a quantity. And so, and I also want to point out, this is exactly what this is for. Like,
Mm.
is this there? Now we've identified a location where we want to look further and examine it at a more absolute way, rather than just trying to pull out the details to visualize. So you can use it sort of like a context imager.
This is something that could be really helpful for Punch as a flow field, start to get some match it to the flow field that starts up at 5 R sun, I think is where Punch starts.
Yeah, 5.4 or something like that. And I'm not exactly sure what mission's going to cover the full middle corona all in one mission, but that'll probably happen one day too. So yeah, this one's great. Another spot to point out is that it's not that different up here, but it's a lot more saturated in the left side than on the right side, where you can see there's sort of a core and then like a halo around it. So again, it's just about trying to take things that are maybe a little bit saturated and desaturating them or undersaturating them. Excuse me. So I can move on, or everybody seems wrapped with these, which I was really hoping for. I spent more time on this slide than on many of the other slides because I wanted to actually make this video. So I'm glad that is a crowd pleaser.
It definitely shows the expansion of the magnetic field in the poles, right?
The super radial expansion.
Super radial
I'm
expansion.
so glad that you talked about that.
Yeah.
So, yeah, what can we do with this now? Like, not just flow tracking, and I've got 10 minutes-ish. Excellent. So there's this thing called the rolling Huff transform. I learned about it first from Ben Bow, and he uses it to track a lot of these things. And I was like, that is the way to go. So basically what the rolling Huff transform is you threshold your image, So say if only there was a nice threshold at 0.5 that you could use, which there is. So then for each of them, you draw a circle, and for every pixel, you put a line through the circle and you count up all of the ones or the zeros, which have you. And then you move the angle and you count it up again, and you change the angle and you count it again. And as you go through, you keep track of which has the most pixels of the color. And you can also do it statistically. It's not just going to be like one, it'll be a little distribution. So you fit that distribution and you find what is the best fit angle for this pixel and its related morphology around it. And then you do that on the inverse, and then you do that on the remainder, and then you do that on a few more times with differently sized circles. And what you end up getting, in this case, this is showing the red, green, and blue channels just show whether it was the positive, the negative, or the remainder that the angle was determined by. So we've got the red and the green are both like high quality angles being found, and the blue stuff is probably not going to be particularly accurate. But then we can turn that into the angle using a typical hue CSV kind of scale. HSV, hue saturation value. Yep. Okay, so what are we looking at? At the pole, we've got radial features, and so the features are the same color as this color wheel. Over here, the features are not radial, and so they don't match their neighbor. And so we can take a subtraction and figure out, okay, if we've got blue, that's a radial feature, and the warmer colors are going to be non-radial features, like the little loop that we've got here. And so then there's a lot more analysis that will happen in my second paper that's coming out about like deprojecting this and comparing it to a model, comparing it to the magnetic field models for the superradial expansion factor. Just in general, there are, including predictive sciences and other excellent groups that do magnetic field modeling. This is from the same time period, and it does have a little thing at the same spot. So I thought that was kind of cool. But so this is a way, I know that is it UComp specifically that measures the magnetic field in a way that it can determine the plane of the sky angle?
Mhm.
So that's the same quantity, I think. as
Same
this.
quantity.
And
yeah.
so I feel like, and Steve Cranmer thinks that it would be a great opportunity to compare those things because they're derived entirely separately from entirely separate physical variables in a way.
The what you get on comp or UComp, the azimuth has a 90-degree ambiguity, so that when you get past a certain Van Vleck angle, it flips 90 degrees. So it'll be like in the poles, it'll be very clear. But it's interesting also to compare to what people who do waves analysis, like see how Young, they're tracking the propagation of waves along field and getting a direction which doesn't have the 90-degree ambiguity, and that should be directly analogous to this. So that's another thing you could compare to. And see how makes those plots. You know that the color table I personally like, because the problem is you can't tell here, like you can tell when it's radial because it's dark, but you can't tell if it's tilting clockwise or counterclockwise. I like the black, red, blue, where black is radial.
Right. Yeah.
And then you can see, because what you see in the and we plot that in the for UComp is that diverging fields have a really clear effect where it's dark in the middle, black in the middle, and then it kind of fans out red and blue kind of softly. Whereas when you have a well, because when you have like a closed field region, you get a much more abrupt type change, and that's partly because of the Van Vleck angle. But in that picture, you can't see that. Is that right? You can't tell.
This is just the super radial amplitude, so it
doesn't have a sign.
That's right.
Yeah. So if you plot that with a sign, you'll have something direct that'll be analogous to this other stuff.
Awesome. Yeah, I admit that this is from the thesis. I haven't redone this work since then, but that's an excellent idea.
And I'm sure I made the same comment then.
And and we're going to talk about just briefly color tables, because I feel like that's the thing that everybody is the moment you've all been waiting for is the color bars, and everyone has their favorite pet color bar.
You just heard mine.
The one thing that I want to mention is just like that there's not really a best method to do this kind of data processing and visualization. It's really what you're looking for. You know, if you're trying to figure out like foreground and background, this thing might be better than if you're just trying to figure out like how wide these things are versus each other, or like, am I trying to study this plasma stuff over here? That might be really good for this feature, but it wouldn't be good for this feature. So the idea is, if you want to either grab my thesis off a shelf somewhere or the paper that I will produce one of these days, I should have like reasons why you might want to pick each one and what it will do to your data, and stuff like that, and some reviews of that. Perceptual uniformity is the thing that is a really big buzzword, I think, in science right now. It's a great thing to do. The problem with most color maps is that they are optimized to look cool rather than to display data in a way that doesn't modify the data. So I've got a couple slides on this, but like you can really see here on the right that like red is a wide region, and then there's a long transition to orange, and then there's a really narrow yellow, wide green, narrow blue, narrow blue. The point is that the colors don't have the same width. So as you start to increment your scalar value to pick one of these a color map is really just like a mapping between an integer and a set of 3 numbers, right? Because it's the RGB value with a given index in that color table. So as you increase the step by 1, you want the irradiance or the lightness, to increase by 1. So that's what's being displayed on the left, with these things being straight lines. As they increment the index, which is sort of the pseudo horizontal axis, the lightness goes up linearly as opposed to being linear. And I could not find an example of this plot for not perceptually uniform color maps. I don't know if they're just too ugly to show or something, but I should probably try to replot that from scratch at some point, because you see that one a lot on the left, but not the inverse. Another way of looking at this is to sort of dither around a value. So if we look at the bottom right, at the top of the figure, like you've got a value that's the primary value that's going across, but as you go up and down, like with a little sine wave on top, the apparent contrast is relatively similar across the entire color, as opposed to here where you lose all of your green, you kind of lose all of your baby blue here, similarly here. So the point is, if you have small details in your image, they're going to get washed out, not by anything but the fact that you're not changing your color very well with respect to your data. Does that make sense?
Yeah.
It's a soft mapping when it should be a more hard mapping, I think. So there's the two things are that you'll have features disappear with the low contrast, and you'll add false features like this yellow edge. There's not anything that's going to happen there at that yellow edge. Like if we look at these two, for instance, the thing on the right, to me, at first, just glancing at it, looks more physically realistic than the thing on the left. The thing on the left, is like a side mold or something, whereas the right one is, I think that these are dunes of some kind. But it's uniform so that you can see that the ridges are all in this yellow. But like over here on the left, you would really expect something to happen at the edge of that. That's just not really a real thing happening. I guess I don't know how to say that better per se, but it's best to have the data be the thing that is changing the lightness rather than the color bar. I also talked to Joe Plowman the other day about the idea that it's nice to have color bars with at least maybe just 2 colors, maybe a third. When you have like jet or something like that, it's got a bunch of colors. You might think like, oh, those are the hotter areas and those are the cooler areas. You'll start to make like assumptions based on the segments. Whereas over here, that's like the green isn't specifically different than the yellow or the blue. It's an intermediate color between them, if that makes sense. So you get a lot of false segmentation, I think, when you use a color bar like this. Similarly here, like what is the black region on these hurricanes? Is it the region where such and such % of rain will fall? It probably isn't, though meteorologically speaking, I suspect that they have a bit more of a calibrated color bar, just so that these are shown standard. Like this could mean maybe snow over here. But that's the thing, is without a description like that, you don't really know what the different regions are. I'm being like led to believe that that black region might be faster, but there's not even any labels on this. It might be rain content or something. So that's just another thing to note. Again, we're sort of coming in for a landing here. So just a couple more slides on colors, and I think that that's it for y'all today. There's different kinds of color maps that can be used. A sequential color map, again, is used for if you're increasing one specific thing, like the absolute value of the superradial angle. That's why I picked one of those, but I think that it's a great point that really what we want to know is just the magnitude in assigned manner in some cases. And so that's what these guys are going to try and do. They give you an average and then you can go in one direction or the other. It's great for Doppler things, like a blue-red. It's great for Doppler. Probably it's okay with temperature, though. You would want to have that be a essentially averaged temperature. Cyclical, multi-sequential. There's just, make sure to use the kind of color bar that's going to really show what you're trying to show. This is another, like, pick the one that works best for your data, not just across the board. It's also worth noting that a lot of people print things out in black and white. You're not going to be able to, like this Buddha one here, the in 3-2 position, is going to be a less good choice than maybe this one here, just because it's not going to have as much contrast when printed. A lot of people print papers still. Another community is the colorblind, which I don't think that I got a picture from, but there's basically 3 kinds of color blindness, and I think it's something like 4% of people are colorblind. So there's definitely a large component of your audience that will not be able to understand your plots or your figures if you don't take account of that. So there's a piece of software called Color Oracle, which I didn't get into this version of the slides, but you basically can hit a command and it will put a mask over your screen and make it look like what a person with that kind of color blindness would see. So there's 3 kinds of color blindness. And if you can make sure you can distinguish the different colors for all 3 of those groups, it opens it up to a significantly wider audience. It's a much more accessible presentation. Also, AI tools are really good at describing images now into text. The first time I took a picture of something and said, "What's in this picture?" They're like, "That person is standing on top of a mountain. Make sure that they don't fall off." I was like, ChatGPT wants me to know that you're in danger. I'll just do for 10 seconds. Generative AI is going to change the world. It's as important as electricity. It's more important than the internet. If you don't look into it, at least if you hate it, that's fine. But like, it's coming, whether you hate it or not. So that's my one little soapbox thing on that. So basically, takeaways from this talk: you have to process your data usually a lot before you can get to something scientifically useful. That includes layers like getting the instrument out, but then like trying to actually visualize the data can be quite difficult. And that's because there's often more features that can be expressed in an image without addressing the dynamic range. You can't just take the average or something normal because you just can't get those 2 numbers to be next to each other without doing something that's coordinate aware, usually in some manner. You definitely don't want to misinterpret things. A great example is that black cloud from the hurricane. I wildly misinterpreted it in real time, even just to show you that it's easy. Pet bugbear. The word false color is falling out of favor, I think. False color like implies that you're showing someone something that's false, whereas if you say representative color, it's representing something that isn't necessarily false. I was at a bar the other day and someone found out I was a scientist and they asked me if I believed in quantum mechanics. So it's just sort of like being clear, I think, with the language, especially with outreach. It's a good call there. And don't try and reinvent the wheel. I don't have the things for you, but use SunPy. If you're going to use Python, it does everything. You can download, you can load, you can make them into movies, you can do all of the filters we talked about today, you can do composite maps. Basically everything that I've shown you today could be done in the SunPy ecosystem. And so that is awesome.
Your stuff, also your.
It's there. I'll even show you.
Right.
It's in quantities are awesome. Fido's awesome. SunKit image is awesome. Oh, I guess I didn't put that there, but yeah, in SunKit image, the wavelet optimized whitening code is there, MSGN is there, NRGF is there, RHEF is there. So any of the major popular ones and also mine are there. So that's what I've got for you today. Thank you for joining me in that. I appreciate it. If you have 1 more minute of questions or discussion time, I'm glad to say hello. But
Yeah, and can you send us that recording too? Because we can get that posted somewhere.
yes, I suspect
Really
that's
good.
there. And it might get
Oh,
sent to you.
might get in here.
There's the cloning.
Oh,
Oh, yeah.
oh, sorry.
Yeah, that's fine. No, it's good. Thank you.
We got you right up against. Thank you so much, Gilly, and people.